This is our second of two spotlight videos to communicate the flavor of enumerative combinatorics, so don't worry if you don't follow every single detail. Let's start with a refresher on permutations. A permutation of the set consisting of the elements 1, 2, 3, all the way up to n is an ordered list of those elements. And here I want to point out this bracketed notation, this bracketed n, that is the notation that I am going to use for the canonical set of size n. That is the set whose elements are the numbers 1 through n. And you probably remember that the total number of permutations is n factorial, which is just n times n minus 1 times n minus 2, and so on, all the way down to 3 times 2 times 1. Now we also have an alternate view of a permutation. We can view it as a bijection from the set of n things to itself. And a bijection is a function that is injective, meaning 1 to 1, and surjective, meaning onto. So here are the 6 permutations of the set 1, 2, 3, first written as lists, and then as functions. And in this two-line notation for a function, we always list the elements in order in the first row. So here 1, 2, 3. And then we write the image of the element below it. So for example, in this function, the element 1 maps to 3, the element 2 maps to 1, and the element 3 maps to 2. Now, saying that 1 maps to 3 is the same thing as saying that element 3 is the first element that appears in the list, and saying that 2 maps to 1 is the same thing as saying that the element 1 is the second one that appears in the list. And finally, we want to know what's the third element that appears in the list. Well, in this case, it is 2. And so we have that the two-line notation function corresponds to the list permutation 3, 1, 2. So another way that we can view this is that there's just an implied 1, 2, 3 sitting on top there. So let's talk about a classic envelope stuffing problem. Suppose that I've written holiday letters to n of my friends, and I've created an addressed envelope for each of them. How many different ways can I put the letters into the envelopes? Well, the answer is n factorial. We are just creating a permutation. We can lay out the envelopes in a line, and then we assign each letter to a place in that line. Now, what if I put an extra condition on the allowed assignments? Let's require that no letter is sent to its intended recipient. So this is the worst case scenario. No letter ended up in the correct envelope. This is called a derangement, and we want to know how many ways there are to do this. Well, here's the answer, and it's complicated. I'm not going to derive this formula for you now, but I promise that we will talk about it in a later video. We will just notice that the answer is an alternating sum. The minus 1 to the k alternates between plus 1 and minus 1. And that's a pretty good sign that we probably use something called inclusion-exclusion in order to find this answer. So inclusion-exclusion is a technique that always ends up giving us one of these alternating sums as our answer. The other thing we will notice in this answer is that there are lots of factorials all over the place. So this is a formula, but it is not a closed formula, meaning that it's not simple. It has a summation sign in it. And in fact, there is no simple formula, which is a little disappointing. But how about the next best thing? Is there a simple approximation? So I want you to look at this sum over here and see if it looks familiar. You've seen a function like this when studying Taylor series in calculus. Do you recognize it? So this sum is the first n plus 1 terms of the Taylor series for the exponential function e to the x, evaluated at x is equal to -1. Now it turns out that the power series for e to the x converges very, very quickly, so this summation is approximately 1 over e, and so that means that the number of derangements of the set of n things is approximately n factorial divided by e. Or in other words, a little more than a third of all permutations are derangements. They have no fixed points whatsoever. So let's extend this insight a bit. Let's pick a random permutation. What's the probability that it is a derangement? And how about the probability that it has exactly one fixed point? Pause the video and come up with answers to these questions in terms of the function d of k, which is the number of derangements of the set of size k. And then use the approximation d of k is equal to k factorial over e to find approximate answers for each. So let's calculate each of these probabilities. The probability that we get a derangement is just the number of derangements divided by the number of permutations, and that's approximately equal to n factorial divided by e over n factorial, and that's equal to 1 over e. All right, so what's the probability that we have one fixed point? Well, we're going to need to come up with a recipe for creating a permutation with exactly one fixed point. And so here's what I'm going to do. I'm going to pick the one element that is going to map to itself, so I can do that in n choose one way. And now I'm going to take a derangement of the rest. And so that can be done in d n minus 1 ways. And I have to divide that whole thing by n factorial. And so this is approximately n times n minus 1 factorial divided by e over n factorial. And so we get 1 over e again. So that's interesting. We are just as likely to get a derangement as we are to have exactly one fixed point. And so now it's your turn. I want you to try to come up with the same sort of probability approximation. So if I pick a random permutation, what's the probability that it has exactly 2 fixed points? And what's the probability that it has exactly s fixed points? So think about this as in terms of a recipe where you're going to have to try to pick the fixed points and then pick a derangement for the rest of the permutation. All right, good luck.